expression requiring lesser number of gates, we use the laws of Boolean algebra or the theorems of Boolean algebra, which we have already studied, which are based on, say, commutative laws, distributive laws, and the De Morgan's law, the duality law. So based on these laws, we convert one expression to another. There are two ways which is popular. There are in fact a lot of ways, and each of these ways are kind of systematic. Like they will use some of the laws of Boolean algebra and systematically reduce. And just to mention that these are not the only ways. There are many different ways you can apply the laws of Boolean algebra and convert one expression to another. But these are pretty systematic. We'll study two of them. One is the Carnot map, which is kind of a visual way which humans are good at. So you kind of draw a map of the logic expressions and then convert one. You represent a expression in Boolean algebra as a map, and then do some transformation of the map to get the reduced expression. This process is pretty intuitive and pretty useful for manual design, but all the designs that are done nowadays are automated because they are very large. They involve very large logic expressions, and for that you need an algorithmic way. You need an algorithm. You need a program which will convert one program into one expression into a reduced expression. So that method is called the Quine-McCluskey method, which is nothing but an algorithm which you can write it down maybe as a C program. And this Quine-McCluskey is primarily the algorithm which is used in all modern circuit design or logic design systems. So whenever people do this so-called VLSI design, they would have a CAD software, computer-aided design software, and the CAD software will have this algorithm built in for minimization. Okay, so we'll do that. And by the way, both these methods, the Quine-McCluskey and the Carnot map method, they are kind of computationally intensive. If you have really large expressions, large number of variables, then this algorithm takes an enormous amount of time. In fact, the Quine-McCluskey minimization can be shown to an NP-complete problem. But to have a tractable solution for large number of variables which are regularly encountered in real-life circuits, you use a lot of heuristics. Use a lot of heuristics to maybe not the optimal solution, but not the smallest circuit possible, but close to a small circuit possible. Use a lot of heuristics. So we'll study some of these heuristics and see how they help you to do the minimization. So this logic minimization, as it stands, it uses some basic laws of Boolean algebra, but it's actually a problem-solving issue. I mean, you are kind of proving a theorem or those kind of. It's a automated theorem proving kind of issue in the domain of Boolean algebra, whatever you have studied. And those are simple because Boolean algebra is relatively simple compared to other arithmetic systems. They are relatively simple. So this is one of the primary area where all these artificial intelligence and other techniques were applied to come up with the minimum logic expression. Okay, so we'll study that. We'll start with the Carnot map. Which, by the way, have you studied Carnot map before? Have you studied K-map before in any of the earlier courses, or maybe in your high school?
So it was in class 12 computer science.
It was in class 12, and
Also in basic electronics.
also in the first year
Yes, sir.
physical electronics. Okay, all right. So we'll quickly go through Karma map, and we'll maybe focus on the Queen McCluskey, which is more algorithmic. So let us share the slide. Just wait. We'll share the slides. Oh, okay. CRM says you will do it, so you just wait a minute. Achha, one more thing. Are there any confusion regarding the theory assignment or the lab assignment?
Yes, sir. Yes, sir. Yes, sir.
What is the issue?
Sir, in question one, part 3, we have to show that is Hamming code a cyclic code or not. But according to the positions of the parity bits and the bits according to our slides, the Hamming code is not shown cyclic, like it is not coming cyclic. But many sources on the internet shows that it is cyclic. So, sir, what should we do?
Okay. All right. So let us do one thing. We'll solve the problem and we'll maybe give you the model solution. You don't do that problem. Everything else you do. And this problem,
Okay.
maybe we'll give you the model solution.
Okay, sir. Thank you,
Yeah,
sir.
yeah, maybe. So basically, but this is pointing to a more serious thing that we'll check whether whatever thing we have given in the slide is it correct or not. We'll do that. Okay. Anything else? Could you upload all the assignment? What about the lab?
Yes, sir.
Yeah.
In the theory assignment, in the fourth question, we are asked to do the reverse double double for taking the last two digits of the member's roll number. So, do we need to form one instance of an 8-digit number or four instances of 2-digit numbers?
Wait. You have to do the reverse. I think you have to take. I'll confirm with CRM. I think you have to take 4 instances of 2-digit. That is what you have to do. Let me
Okay,
look
sir.
up the statement once. And yeah, I think that is 4 instances of. That's
So,
all
sir,
that you have to
only
do.
like four double doubles of four reverse double doubles of
Right.
2-digit
Right.
numbers. Okay, sir.
Right. Exactly.
Yes, sir. Thank you, sir.
And that is equivalent. In fact, it will give you the same result. Okay. And in the lab, is there any problem with the lab assignment? What about the lab assignment? Is it okay? Any other problem? Could you submit? To submit the lab assignments?
Yes, sir.
Okay. Okay. All right. I think I'll ask CRM to start.
Sir,
Yes. Tell. Yes. Tell.
Sir, sir, in question 6, it is written that we have to consider sets and the intersections of them and their complements. So, sir, I'm not clear as to whether we need to take complements of the individual sets or whether we need to take the complements of the intersections of those sets.
I think complement of the intersection. You have to take a complement of the intersection.
Yeah, hello. Hello.
Yes, sir.
Yeah, hello. Am I audible?
Yes, sir.
Okay. Yeah, sorry, I got a bit late. So, Pavitra, will I start? Okay. Um, so, hello. Hello. Okay, I'm sharing my screen. Is it okay? Recording has started. Fine. So, I'm sharing. So, today we shall look at Kano maps. Okay. Just wait, I'll have to again restart it. Okay. Yeah. So today we'll be looking. I've already given you a notion of the Skarno maps. Skarno maps are a way to the Karno map method is a way to minimize small Boolean functions manually. So the primary objective is to minimize a two-level sum of product form of Boolean expression, but it is equally applicable to product of sum. So we'll look at that towards the end. So I've already explained the basic principle. This is the basic principle of minimization. That means if two product terms differ in one literal, then that literal can be eliminated. All right. So here is a diagram of a Karno map. Okay, so I think the first step is to really understand the diagram. Okay. So this one is a slightly bigger one. Let me draw the diagram for a much smaller Karno map. So suppose you have just two variables, let us say. Let us say A and B. Say A and B. Then this can have two values, say 0, 1 and 0, 1, right? So these blocks, these refer to A bar, B bar. Then this one refers to A bar, B. This one refers to AB bar, and this one refers to AB. All right. So this is the basic thing. Let me just put it this way. All right. Now, suppose we extend it. Suppose we have A, B, C. All right. We want to add another variable. Then we can extend it. All right. So now here, when you're extending it, of course, let me put it this way. Well, although I've put C on the this thing, so let me, so I'm putting 0 here, and 1, and this I reflect. Okay, So this I reflect just like gray code. Put a 0 here. All right. So now on extension, this square is now A bar, B bar, C bar. So, or maybe just to make it a little easier, I just extend this. A bar, B bar, C bar. So here also it is A bar, B bar, C bar. Here it is. Okay, now here it is still A bar, but now it is B bar. It is B bar C. Okay, it is B bar C. And this one is and these are, so here it is of course A bar, here B's B C C, and this one is A bar B C bar, this one is A B C, and this is A B C bar. All right, so what you can see, the important thing to note is that the principle of gray code has been used. So which are adjacent? Okay, so these these are adjacent. I mean the adjacent ones are adjacent basically. So these are adjacent. These are adjacent. More interestingly, these are adjacent. And also, these are adjacent. So all the squares are adjacent. All right, so these are adjacent means that these mean terms, if you have a mean term here and a mean term here, you can combine them together. So now let us see this example. So I think you can easily relate this diagram to the diagram that we have drawn. So here you see CD, we write 0, 0, 0, 1, 1, 1, 1, 0. So you can see that, the here also you can see that this is playing out this way. All right. This is a gray code principle which is working. So it is convenient to number this these squares. Okay. Why is it convenient? Because these mean terms are often represented with the numbers. Okay, so this one, say A bar, B bar, C bar, D bar, this one is numbered as 0. So this one A bar, B, C, D, this is numbered as 7. All right, so it's a little more compact. So this is how it's often written, and this is the notation. So this M represents mean terms. So it's a sum over mean terms. Okay, there's a sum or. Okay, so this is sum over these mean terms, and these mean terms are also shown over here. So this is 0, this is 7, this is 9, this is 12, and this is 15. Now, this is a Carnot map. So these are mean terms. If you look at this carefully, only 7 and 5 are adjacent. All right. Only these two mean terms are adjacent. You don't have any other mean terms that are adjacent. So let us see what these mean terms correspond to. So this 7 and 15, 7 and 15. So let us see. So 7 is A bar, B, C, D, and 15 is, of course, all of them are 1. So A, B, C, D. So as you can see, this is, if you like, we can just write it like this. So the point to note is that they differ in one place, okay, and that is dropped. That is dropped. So this gets eliminated, all right. This gets eliminated. So that is how you minimize. Okay, so this is a simple example where you have only pair of mean terms that are adjacent to each other, that are adjacent, 7 and 15. All right, so is this okay with you? This is, I mean, once you understand this, the rest is quite straightforward. So have you understood this? Hello? Or does anyone have a question here? Hello? Yes? Are you okay with this? Anubhav, Dhad, are you okay with this?
Yes, sir.
Anubhav? Huh?
Yes, sir.
All right. Okay, so this is the basic idea. So now let us move on to an example. Yeah, so whatever. Yeah, okay. All right, so it is best for you to, okay, this is the same example. So this is the mean term. Yeah, so the other ones are singleton mean terms, so you are not able to minimize those. So this is um, the result. So as we saw, on combining 7 and 15, we got BCD, and then these are the other mean terms. Okay. Now here is another example. I think it is best for you to just try to do it on your own. Of course, the solution is there in the slide. So I'll give you a few minutes. Just work out on your own. You have seen how it is. It is a simple method. So just try doing it on your own. All right. Okay. I'll just wait for some time. Yeah, okay. So let us just see the solution. You you might have done it yourselves. So uh, this is very evident, right? You got a big block here. All of these can be, grouped together. Then you got another nice block over here. It's not as big as the earlier one. Earlier one had 8 terms. This one got 4 terms. All right. And then you got some options with 2. I mean, you could group 2 with 6, or you could say group 2 with 0. Both are possible, and both of them give you the solution with same cost. Okay, and I don't think any further grouping is possible.
Instead of grouping only 2 and 0, can we group 2, 6, 0, 4?
Oh yeah, sorry. Yeah, I just noticed that. Yeah, sorry about that. Yeah, in fact, that's right. So you get, yeah, this is the thing. So you can group it like this. Yeah, exactly. You can group it like this. Or rather, instead of going in there. Yeah, that's right. So this gives you a better, yeah. So these are the terms. So let us just see what we have there. So this one, oh yeah, right. So you have this and you have this also. Okay. So these are your terms, and you can write down the corresponding expressions. So as you can see, this is something that I had mentioned to you long back, that so these are called cubes, by the way. I mean, these are called cubes. This product terms, these are product terms, or cubes. So I mean, you can think of those as hypercubes. So what you see is that bigger the cube, smaller the product. Okay. So so C1 is the biggest cube here. All right. So now this is another example. Anyway, so you can just try this out. This is another example. Let me see. I hope I will not miss out. So I think these seem to be the only good cubes. I mean, things that you can group, you can expand. So let us see the solution. This one, this one. All right. And you can, of course, write out the expression. So just write out the expression also. So you can write out the expression, right? As usual, bigger the cube, smaller the product. So these are your, this is your reduced SOP, okay? Reduced SOP. Of course, I mean, do you notice something something awkward about it? Or let me try to explain with an example. So suppose you have, suppose my sum of product is suppose this is my sum of product. It's not hard to see that this is just one, right? So what you find is that the input is highly inefficient. That means in the worst case, your input itself can be of exponential size, even when the output is kind of very is a very simple function such as this one. All right. So this is a very basic problem with this when you try to address the minimization of Boolean functions. So the mean term representation, the sum of mean terms, that is of course theoretically it's a very nice method. You can uniquely represent your functions, but it has this problem that it's a fairly bad way, probably the worst way of giving your input. All right, it's probably the worst way of giving your input. So in fact, the actual CAD tools, CAD means computer aided design for for designing electronic circuits or systems. Those often don't take the input. I mean, those can take the input in this form, but they usually don't take the input in this form. I mean, they don't need the input to be in a canonical form, because the problem here is that problem here is with the canonicity. All right. CAD tools usually start with a cover, okay, with a cover. So what you have now is of course a cover, okay. These 4 blocks here, for example, these are covering all your mean terms, and of course these are covering all your mean terms. All right. So you could start off with a suboptimal cover, and from that you could try to get an optimal cover. So usually when you are designing circuits, you can often represent because in the process of designing, in fact, your first experiment was to come up with Boolean expressions to capture various situations, right? So when you are forming Boolean expressions, you are really you're really forming a cover of your function, which may not be optimal, but it's still a cover. So in fact, that can be a starting point uh, for your logic optimization. And then we could following suitable methods, you could try to optimize that. All right, so so let us, if we get the time, we might touch upon that. But anyway, so let us carry on with this example. So this is a bigger example. As you can see, this get bigger. The map gets bigger. Obviously, it doubles in size for every variable that is introduced. All right. So this one is your map, and we also numbered the cells. So this is how your mean terms are distributed. So now, can you try to optimize your optimize the expression? Is someone trying to say something? Yeah, can you try to optimize this? So note that, I mean, this is of course a very obvious grouping, or maybe we can just, the important thing to note is that, this column and this column, this can be grouped together, because if you see, this and this are differing by exactly 1 bit. Alright, so let us just say this is one, this one is quite obvious, this is another, and so do you see any other interesting grouping? So 24, 26, 30 and 28, okay, you can group those also. And well, actually, I think I have I missed? Yeah, okay. Yeah, I think that's it. Yeah. So these are the groupings of these meters which allow you to minimize this function. So you can write out the result. All right. Let us take another example where you have don't cares. Okay. So note the this part. These are your don't care terms. That means this don't care terms are indicated here. Okay. These are indicated here. So while you have to, so these are called don't cares, and well, these are the essential terms or care terms, if you like. Okay, so this blue, when you construct your cover, these blue terms are the essential mean terms. These have to be covered. If you don't cover this, you don't get a your cover will not be equivalent to the original function. But with regards to the don't care terms, you have an option. That means you take them only if that helps you. All right. So now let us see how this don't care terms can help you. So this particular cube only has care terms. But now if you look at this one, there the don't care terms are helping you to expand that cube. All right. This one, of course, is built only with the care terms. But now this one, the 19 has helped you there, and well, 20 and 21 over there. So, I think, I hope you understand the use of this don't care terms to facilitate the building of your cover. So again, from where do you get the don't care term? So when you construct your Boolean function, at that time only uh, you realize that some of the mean terms are essential and some of them don't care. That means it really doesn't matter whether you include them. Oh, there is another one, 6 and 7. Yeah, so it doesn't really matter whether you include them or not. So as you can see, all these blue terms have been covered, but 18 and 31 have been left out. So those are don't care. So you don't have to include those. You include them only if that helps you to expand a cube. Okay. So now you can of course write out the product terms corresponding to these cubes. So these are the product terms. All right. Here is another example. So just do it on your own. This is another example. Just do it on your own. I'll give you a few minutes. Why don't you do this example on your own? So make use of the don't care terms uh, uh, to expand cubes as far as possible. Okay, so let us just see the solution. Yeah, let's just see the solution. So there's a nice cube over there, quite a big one, and then of course you have this one is of course the second one only, or rather it doesn't rely on any don't get terms. This one is also done without any don't get terms. Yeah, so that's all. So you have used only one don't get term. All right, used only one don't get term. So anyway, so I think this principle is quite clear to you. Any questions here from anyone? Yeah, any questions here from anyone?
Sir, how do we decide that some terms are don't care terms?
Yeah, it's given. See, it's given here. It's given right here. Okay. Is
Sir,
that okay? Huh?
sir, also for selecting rows, the difference between the row numbers should be 3.
Sorry?
Sorry,
30?
selecting the columns, sir.
Huh? Yeah, what's
The
the
difference
issue?
the difference between them should be 3. Like for example, we have
No,
taken
no. They should differ in only one bit.
only yes, sir. Okay.
See the basic principle I told you in the first slide. That is the same principle which is used everywhere. They should differ in only one bit. Okay. All right. Any other questions? Okay then. So let's move on to the next one. Oh well, here is a bigger example. So you can work this out also. Why don't you work this out? There's another example for you to work out. So as you can see that it starts getting unwieldy. I mean, you can keep on expanding. You can keep on expanding. You can keep on expanding the map recursively by adding, variables. But it gets unwieldy. Anyway, so this is another example. Why don't you just try to work this out? No, don't get terms here. So I'll give you a few minutes. Why don't you work this out? Okay, so these are the cubes which can be found. Okay, 15 is an isolated cube. That's another bigger cube, and with these all are covered. Okay. All right. So you have seen examples of using Carnot maps up to 6 variables. Of course, you can take it to 7 variables, but that just makes it more and more difficult. Okay, you got to draw so many squares, and you got to also number those carefully. So that's that becomes more error prone. So it becomes very cumbersome. Can be done, but that is when we prefer to move on to other methods. Anyway, so up to 6 variables, you probably it's not too bad. All right, so we have looked at minimization with mean terms. Now it is also possible to minimize with max terms. Okay, so here you have an expression with max terms. Now note that there is a certain convention which is used. So let us see, if you look at the first max term, A or B or C bar or D bar, okay? So that is coded as 0011. In other words, if a variable is complemented, it is taken as, the position is taken as 1, and if it is uncomplemented, that position is taken as 0. So we'll also, anyway, so the direct minimization it follows the same principle as before. Now note that we can use the Carnot map minimization method. We can use the Carnot map minimization method also to optimize the complement of a function. So sometimes it is convenient. So instead of minimizing the function, it might be convenient to minimize the complement of that function. So so suppose, I have here if rather I should have called it G, I think. I just wrote it as F. Oh, okay. Not really. This is okay. Suppose, okay, I could have written it as G. It is not so obvious that it is F. So anyway, I just take it as a sum of this main terms. So what you can see is that these are the so suppose this is your function. Suppose this is your function. This is this corresponds to this now if you complement it, this is what you get. I've just taken the complementary mean terms. So this is what I get. Now, this can be written as a complement of the max terms. Okay, so let us take one example. So, what is M3? M3 is 0, 0, 1, 1. All right, corresponding to A bar, B bar, CD. What is M3 bar? So M3 bar, you can take the complement of this, and that corresponds to okay, and this one corresponds to M3. All right, so this is the relation between these. So that is why we have this kind of convention, so that in M3 bar corresponds to this max term. All right, so that is what we have written. So of course you can see M3 bar will correspond to M3. All right, capital M3 bar will correspond to M3. So this one, for example, corresponds to M3. All right, so on. And now if you take F, this is what it is. I mean, of course, this is maybe I should not write this. It is just M3, you know. Oh yeah, sorry. No, M3 bar, it is all right. So it is, yeah, M3 bar corresponds to, that's right. M3 bar corresponds to M3. And then if we take F, this is what you get, all right, which is in fact this. So maybe I should really have started with G. I should really have started with G, that would be better. So, and right, G bar is equal to F. All right, anyway, so what it means is that but the minimization as such, as you can see over here, the minimization is is done in the same way. Okay, when you're minimizing with these, you're doing it in the same way. You're doing it in the same way. So if you want to minimize a function through its complement, that's when you can. That's when you can use you can use this Carnot map over max terms. Independently, if you have a function given to you in this form, you can still use the Carnot map in this form. Okay. So is that okay? Any questions on this part?
Sir, what is capital M here? Like capital M3, capital M4?
Yes. So this is capital M3.
Okay.
This is capital M4. These are all max terms. All right.
Yes.
All right. Any other questions? Hello. All right. So I think that is you can just write down the terms. These are the uh, sums. This is a product of sum, as you can see. Yeah, this is a product of sum. All right. Okay, yeah. So here is another example. So why don't you work out this example? Yes, sir. So this is given to you as a product of sum. So you're basically oh, I think yeah. So this is given to you as a product of sum. Yeah, okay. So you can just try to do it in the same way. Why don't you try to do it that way? So just note that it is this product of sum. This is the, and here M is capital, meaning max terms. So just try to work it out. It's not so difficult. It's the same kind of thing. So anyway, I'll just show it. All right. And you can write out. So just be a bit careful here, this convention. All right. Need to be a bit careful. Okay. So that's it. So this is our treatment of corner maps. Note that you can use don't cares in the same way here. Don't cares can be used in the same way. All right. Okay. So okay. All right. You can just take a break for a few minutes, maybe 5 minutes. Then we can go over to the next topic. Okay. Let us have a break of 5 minutes. Involving all of the sets. Involving all of the sets.
Okay. And sir, one more doubt I had, like, sir, we have 4 members in the group. Then in which order do we have to form these 8 digits? Like, there can
You
be many
can form in
combinations.
any order, doesn't matter.
Okay. Okay.
Sir, I also had doubt in question 1, part 3, sir.
So I think, Pavitra, do you want to share your screen again?
Yeah, I'm doing that. It is question 1. Wait a minute.
Part 3, sir.
Yeah, you can share yours. I mean, I can also share.
No, I'm sharing.
Okay.
Can you see the screen?
Not yet. Just I'm getting a.
Sir, in the part 1, question 1, part 3, sir, if we put the bits according to
I know.
Yeah. Okay. So, what is the issue? Hello.
So in question 1, part 3.
Yeah, it's a question. You have to answer it.
No. The thing is that what internet says is that Hamming code is a cyclic code, but if you apply the rules, the criteria that are discussed in class, then it is not a Hamming code, not a cyclic code.
No, why do you say so?
So can you please answer? Can you please
Sir, like if we go with the slides and put the parity bits at the positions 1, 2, 4, 8, then we find that Hamming codes are not cyclic. But when we are surfing the net and other resources, we come to realize that Hamming codes don't have a unique way of representation. Like you can arrange the parity bits.
So why don't you answer that way? I mean, why don't you answer that way?
No, so we are confirming whether this statement is right or there is a fixed way of representing a Hamming code.
No. Why don't you take it as a question and just answer it to the best of your ability? So, if you have already seen that it's a cyclic code, then you just have to give a proof that okay, it is cyclic. That's all. So, whatever assumptions you need to make for that proof, you can state those assumptions. Okay.
Okay, sir. Okay.
All right. Yeah.
Okay. So I think we can start with this.
Okay then. Yeah.
Yeah.
Hello.
Yes, sir. Hello.
Yeah. Tell us.
Yes. Should we give Are we supposed to give mathematical proofs or just a theoretical understanding will do?
See, it should be adequately rigorous. I'll put it that way. Okay.
Okay.
Yeah. All right then, Pavitra,
Okay.
do you
So
want to?
we can start.
Yeah. Okay. Thanks.
All right. So we'll talk about an algorithmic method, a systematic method of reducing Boolean algebra expression. It's called the Quinn-McCluskey method. Okay. So
yeah, Pavitra, let me just give a little bit of introduction.
Yeah, maybe you can.
See, while discussing Karnaugh maps, I mentioned that Karnaugh maps are suitable for human optimization. So you arrange the mean terms using the principles of gray code, so that adjacent terms are easily identifiable. All right. That is the idea of this Karnaugh map, and as you have seen, you can apply manual optimization, but you can't go very far. I mean, first of all, if it is done manually, it's only as fast as you can do it. Our computers are much faster, and also manually you can't go very far. So this Quinn-McCluskey method is a an algorithmic method. I mean, even Karnaugh map is algorithmic, but it is better suited to. So this is a Quinn-McCluskey method is better suited to programming. Okay. In fact, Karnaugh map also, if you try to program, you'll get something like this only. But people don't usually try to port this Karnaugh map method. So this is a step-by-step method which essentially forms it combines it starts bottom up, because your input is again in the form of sum of product, canonical sum of products. That means the sum of mean terms. You might have don't get terms also. So the principle is to go bottom up. That means you combine adjacent terms to form bigger terms, okay, or rather adjacent cubes. So the smallest cubes are your mean terms. So you can combine your mean terms. So if you combine two mean terms, you eliminate one variable. Then if you combine two, because these have to always differ in one variable. So if you combine, if you call this mean terms level 0. So if you combine level 0 terms to get a level 1 term, you can eliminate one variable. Two level 1 terms to a level 2 term, you eliminate another variable, because in each step you are eliminating one variable. So like that, you develop. You get a set of terms, so each of these are called implicants, because a mean term is obviously an implicant. So whenever the mean term is true, the function is true. So similarly, any of these products are implicants. So at some point, you cannot make a product a cube any bigger. So it's easy to this is the usual thing, that you cannot expand a cube anymore. So when you can't expand a cube anymore, that is called a prime cube, or also a prime implicant. Okay. So these are the biggest cubes that you can form this way. So now your aim is to cover. In Karnaugh map also you are forming a cover. So here also your aim is to get a cover of the function, of all the mean terms in the function, using the prime cubes or the prime implicants. Okay, so that is really what this Quinn-McCluskey method is. So I think now you can look at the steps in some more detail. Okay, thank you, Pavitra. Yeah.
Yes. So basically, there are two steps in the Quinn-McCluskey, as Professor CRM has discussed. There are two steps. It's a bottom up. So let us first describe the method, and then what we'll do, we'll explain with examples. Okay. All right. So you have the cubes, and you put them into two groups. Let's say there are m number of cubes which are in the on set, and n number of groups which are in the don't care set. Okay, and then what you do, you combine the adjacent terms between the group. So basically, when their positions match, positions of the ones, the onsets and the don't care match to get the prime implicant. Okay, so then, so see, the whole idea of this logic minimization, whatever, is that if you write down the onset and the don't care set, you have to cover all the onset minterms. You have to cover all the onset. You have that's compulsory. You have to cover all the onset minterms, and you can, if you want, cover the don't care terms also, don't care minterms also. Right. So what we do is that first we create an implicant table. We create a table of implicants. Then you reduce the tables by some rules, which are kind of, denoting logic equivalences. These rules are in terms of row dominance and column dominance. Okay. So you do this, you use this row dominance, column dominance, and reduce these tables. Reduce these tables of the implicants. All right. So then there are, so in this way you identify something called an essential prime minterms, or then you keep only them. So let us explain it by a method. Okay. So let's say it is a function of 4 variables, and it is a summation over the minterms 0, 5, 8, 9. So this 0, 5, 8, 9 are the numbers we discussed in the discussion for the Carnot map. So let us see what happens. Okay, so let us look at this 0 term. So it is a on term, and there is no don't care term. So if we look at m equal to 0, what are the values of the variables? It is all 0. Similarly, if we look at the min term 8, these are the variables a, b, c, d. So here we have 2 min terms. So if we combine these to cube, what do we get? If we combine these to cube, what do we get? We get this a is differing, so you can reduce, you can eliminate a, and you have b, c, d. You have, in fact, you have b prime, c prime, d prime. You have b, c, d. Okay, so these two we are combining. So this is a kind of 0 level in terms, you can say, and these we have combined. All right. So what are the second level min terms that we want to combine with? So this is 8. This is the min term 8, and you have the variable values 1, 0, 0, 0. And let's say if we can combine with the min terms 5, 9, and 10. So which are these values of the variable? So what happens? So if you combine 8 with 9, you get, let's see, they can be combined or not. So basically, see, we are kind of checking one min term with all the other min terms. We are kind of checking one min terms. So basically, we are looking at pairs of min term, and this you can see is nothing but a loop in a program. So that we are doing, and then let's see. So this can be combined, and this is what we get in the result. Similarly, this can be combined. This is what we get in the result. Now let us look at these 3, and let's see if we can combine with the other 2, that is 11 and 14, the other 2 min terms. So we see that 9 and 11 can be combined, and this is what we get. 9 and 11 we can, so similarly 10 and 11 we can also combine, 10 and 14 we can also combine. Okay, and we can get a reduction because of that. So now let us look at the other possibilities, like can the other pairs be combined? So let us look at 11 and 14, and let us look at 15. So we see that 11 and 15 can be combined, and this is the reduction. Similarly, 14 and 15 can be combined, and this is the reduction. Okay, so now let us go to the second level. So now we have these pairs. I'll explain this in more detail. I am just walking through the algorithm. I'll explain what are the formal steps. I'm just giving an example right now. Okay, so now let us look at these two-level minterms. That means two cubes combined, 8, 9, and 8, 10, let's say, and these will be the variables. And these are the other two-level two cubes consisting of two minterm, 9, 11, 10, 11, 10, 14. And these are their variables. Now we see that these two can be combined. So see, the idea of the algorithm is like that. So initially, so this is your function. This is your function. This is the set of minterms given to you. So at first level, what you do is that you try to every singleton minterms you try to combine with each other. And the combination rule is same as long as if there are 4 variables or if there are k variables, if k minus 1 variables are identical, and the one of the variable is complemented, then you can combine it and drop the complemented variable. The same law as the Carnot map. Okay, so what we are doing here is that at the first level we are individually combine them. We are checking in a loop whether, let's say, 0 and 5 can be combined, 5 and 8 can be combined, 9 and 10 can be combined, 11 and 14 can be combined. We just check them. In fact, as you can understand that what can be combined with what for a particular number of variables, they are kind of a lookup table. You can easily recall it from a lookup table. You need not actually compare them. So you first level you check every pair that can be combined in the sense that that variable at least one variable can be dropped. Then you formed after whatever can be combined, you form pairs. Then look at the set of all pairs. So it's like a tree structure we are building. Then look at all pairs, and then you see what pairs can be combined into cubes of size 4. And then you get some valid cubes of size 4. And then after that, you try to combine cubes of size 4 to get cubes of size 8, which is again you run a loop over the set of all. So if you look at it, the idea is something like this. It's kind of grouping the variables together. Grouping the not the variables, grouping the minterms together. Okay. So wait, let me try to just try to this will do. Okay, so basically you have a set of minterms. Available with you. Let's call it M1, M2 up to MK, let's say. So you try to check for every pair whether they can be combined or not. Okay, so then you form pairs. Let's say these are some of the pairs that got combined among the existing minterms in the logic expression. Okay, then you try to combine this to get even higher level. Try to combine from sets of whatever possible combinations are there. Then maybe you try to combine to form even larger sets. Okay, and so on. Okay, so this is the entire process. So what you see is that, and fine, and what is the combination rule? Combination rule is very simple. If you have one mi, let's say the variables a, b, c, d, they just, and they're mj. So it is just one variable which they differ in. So if you combine MIMJ, you will basically get A bar, B bar, C. That's what you get. Okay, which is another min term involving 3 variables. So this way, and when you are checking whether this MIMJ is combinable with say MUMV, then you just check for this. So MUMV will have some other set of variable, you just check whether these two are combinable or not. So this way you keep on combining, and the higher the level you can go to, more reduction you have, more number of variables you have eliminated. More number of variables you have eliminated. Okay, and you see it's very algorithmic in the sense that all you need to do is to have a outer loop over the levels and an inner loop at each level over the set of minterms or the set of cubes that you have at that level. You run a loop over that. So just 2 loops are sufficient. Of course, you have several ways of reducing this. So what you do by this process, you come up with a set of implicants, And one thing is not guaranteed in this process is that the set of implicants there. So the final set of cubes or implicants, so some cubes will not be combinable. So for example, there is one cube here which is not combinable. So you retain all of them. And this is something that is not. So your final set of implicants will be this, 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 and this. Whatever set of cubes cannot be reduced further, cannot be combined further with anybody else. Those are your set of implicants. So they may be of varying size. Okay. So what you get, I'll explain this formally in the next class. So what you get in this process is that you get a set of implicants. Which you write down as a chart. But what is not guaranteed is that these implicants are kind of enough. If you have all of them, you are definitely having the same function. You are definitely having the same. It covers the entire function. This set of implicants that you get in this process covers the entire function. You have the complete function. But what is not guaranteed is this the minimum function? Is this the minimal function? It is the smallest function which covers the original function. So for that, we have to go to the second step of Quine-McCluskey, where some rules are used. To kind of find out from this entire set of implicants to find out the smallest set of implicants. So that's how it goes. This is the process. So what you finally have is kind of a table like this. So in the rows of the table, you have the unreduced or not further reducible implicants. And in the columns, you have the minterms. And these things imply whether they are covering that this implicants, whether they are covering that minterm or not. And based on these cross marks on this table, we apply some rules to discard some of the rows. Okay. So because you see every row in this implicant corresponds to a term in the function. So if you can reduce the number of rows, you can reduce the number of terms in the expression. So what we'll do is that we'll explain this in detail. So I think let us stop today. I'll formally explain this in detail in the next class, and then we'll see. Okay, so let us stop today.